Today we will be talking about scheduling policies. We will walk through some examples of different scheduling policies to demonstrate the difference between them. Before we jump right into the topic, we have to understand what problem is solved by scheduling policies. As you may know, CPU uses time sharing to increase interactivity and reduces CPU idle time. CPU achieves this by running one process for a while and then stop it and running another one and keep switching between different processes. In this way, CPU could switch to another process while one process is blocked by I/O. Therefore, it keeps CPU running at full speed and reduces CPU idle time. However, this does not come without any cost. Switching between different processes may create a overhead and thus reduces CPU performance. Now we know that operating system is constantly switching between processes, but how does operating system decide which process to run? Here comes the main point we will talk about today, scheduling policies. We will be looking at three scheduling policies in detail today. They are first in, first out policy, shortest job first policy, and round robin policy. There also exist many other policies that's more advanced, for example, multi-level feedback queue or lottery scheduling, but we will not be covering them today. There are two metrics to help us to measure the performance of scheduling policies. They are turnaround time and response time. Turnaround time measures the time between arrival of the task and completion of the task, and response time measures the time between a task is first scheduled and the time the task arrived. A good response time means that user will wait less time before it first get any feedback, so it improves interactivity. And a low average turnaround time means that on average, every task takes less time to finish. So our objective is to minimize both turnaround time and response time. Now let's look at our first scheduling policy example, first in, first out policy, or sometimes first come, first serve policy. It is the simplest scheduling policy you could ever imagine. You just schedule the jobs in the order of their arrival, and does not optimize either turnaround time or response time. Now let's look at a specific example of first in, first out policy. Suppose you have two tasks, A and B, and their CPU burst and I/O time are shown in the diagram. Since A arrives first, it will be scheduled first, and it will run for 4 seconds until it finishes its first CPU burst. Then process B will be scheduled and A will do its I/O. At t equals 6, A will finish its I/O and be queued after B. At t equals 7, B will finish its CPU burst and A will be scheduled. At t equals 8, A finishes, and at t equals 10, B will finish its I/O and B will be scheduled. At t equals 12, every task is finished. Now let's look at shortest time to completion first policy. It will schedule the job that has shortest time to completion. This policy optimizes the average turnaround time. We have the same two processes A and B, but this time with shortest time to completion first policy. At t equals 1, A arrives and it will be scheduled immediately. And at t equals 2, B arrives. A has 3 seconds till it finishes and B has 2 seconds till it finishes. So B will be scheduled now. At t equals 4, B will finish its first CPU burst and goes into I/O. A will be scheduled again. At t equals 7, B will finish its I/O, and at the same time A will finish its first CPU burst, so A will go into I/O and B will be scheduled again. At t equals 8, A will finish its I/O. Since it only has 1 second till completion, it will be scheduled. At t equals 9, A finishes and B is scheduled again. And at t equals 10, all tasks finish. Now let's look at our last scheduling policy, round-robin policy. With round-robin policy, we run a job for a time slice and then switches to the next job in the queue. In this way, every job will get a chance to run very quickly, and it does optimize the response time. Let's now look at our same example with round-robin policy with 2-second time quanta. So when A arrives at t equals 1, it will be scheduled immediately. At t equals 3, A finishes its time quanta and we switch to task B. At t equals 5, B finishes first CPU burst and goes into I/O. A will be scheduled again. At t equals 6, A finishes first CPU burst. At t equals 8, B finishes I/O. A can now do its I/O and B will be scheduled. At t equals 9, A finishes I/O and A will be queued after B. At t equals 10, B finishes 2-second time quanta and A will be scheduled. At t equals 11, A finishes and B will be scheduled. And at t equals 12, every job finishes. As we can see in these three examples, different scheduling policies focus on optimizing different aspects. However, in a real operating system, things would be more complicated since we don't know how long a process will run for.